Next chapter does. Now consider this rectangle ABCD and its image A prime, B prime, C prime, D prime. In this example, the rectangle has been translated or moved. Or we can say that the vertices of the rectangle A, B, C and D have been translated, moved or slid to the points A prime, B prime, C prime and D prime. The image has been moved up and to the right. When an object is translated, each point on the object moves the same distance and in the same direction. Therefore, we can describe a translation only if we know the distances moved and the direction of motion. In this case, each point was moved 9 places to the right and 4 places up. A quantity that describes the distance and direction of motion is called a displacement vector or simply a vector. The distance moved is the length of the vector and it's called the magnitude of the vector. Examples of vector quantities include velocity, acceleration and force. Quantities such as mass, time, height and temperature only indicate magnitude but no direction. Such are called scalar quantities. A vector is represented by a directed line as shown on your screen. The direction of the vector from A to B is shown by an arrow and its magnitude is the length of the line AB. Vector AB is written as AB with a waveline below or AB with an arrow on top or simply a bold AB. Its magnitude is denoted by AB with a waveline below and 2 vertical lines. A is the initial point, sometimes called the tail, and B is the terminal point, called the head of the vector. Sometimes a vector can be denoted by a single small letter as shown on your screen. In printed work, vectors are denoted by bold letters. When writing these vectors, you will use the common notation AB with a waveline or simply a small a with a waveline below. Equivalent vectors. Now vectors are equal if they have the same magnitude and same direction. In these examples, vector PQ is equal to vector RS. Vector A is equal to vector B. Also notice that vectors P and R have the same magnitude but opposite directions. We say that vector P is equal to minus vector R. Next, translation. A translation is a transformation that moves an object from one place to another without turning it or changing its size or shape. Translation is done using what we call column vectors on a grid. Column vectors tell us exactly how the object needs to move. It is exactly like normal coordinates where we have an x and y coordinate. The top number is the x coordinate and the bottom number is the y coordinate. Coordinate tells us how far left or right the object moves. If we have a positive value, that means the shape moves to the right, and if we have a negative value, that means the shape will move to the left. The y coordinate tells us how far up or down the object moves. A positive number means the shape moves up, and a negative number means a downward movement. Notice that the figures do not change in their shape or size. So if we want to translate triangle A with vector -2, 3, we can easily locate the image. A quick way is to pick a single point on the shape, like this, and we use it as our starting point. we look at the x-coordinate to see how far right or left we have to move. And then we look at the y-coordinate to see how far up or down we have to move. In this case, we move 2 steps leftwards and then 3 steps upwards. And that's where our point will be. Now we can draw our original shape around this point because the size does not change and neither does the shape. Translations can also be done by calculation. All we need to do is to add the translation vector to the coordinates of the points given. For example, triangle PQR with coordinates P minus 2, 1, Q minus 3, 2, and R minus 3, 4 undergoes a translation with vector 3, 2. Find the coordinates of its image. We simply work. P plus the translation vector will give us P prime, the image of P. Then we write the coordinates as column vectors and add them. Minus 2, 1 plus 3, 2 will give us minus 2 plus 3 is equal to 1. 1 plus 2 is equal to 3. And so we have P prime 1, 3. Again, for Q, minus 3, 2 plus 3, 2 is equal to minus 3 plus 3 is 0. 2 plus 2 is equal to 4. And so Q prime is 0, 4. Finally, R, minus 3, 4 plus 3, 2. Minus 3 plus 3 is 0. 4 plus 2 is 6. And so R prime is 0, 6. And here are the coordinates of the image. Given an object and its image, we can find the translation vector. Shapes A and B are identical. Describe the translation of shape A to B. What we do is pick a single point again and then track how far down it has moved to shape B. Recall that right is positive and left is negative. Then up is positive and down is negative. In this case, on the x-axis, we moved plus 4 places. And along the y-axis, we move minus 6 places. The translation vector will be 4 minus 6. Using calculations, we can also find the translation vectors. For example, our point B, 5 minus 7, is mapped onto B prime, negative 3, 5, under a translation T. Find the vector T. So we know that B plus translation vector T is equal to B prime, and therefore T is equal to B prime minus B. Let's give T the coordinates xy, and so xy is equal to minus 3, 5 minus 5 minus 7. Minus 3 minus 5 is minus 8. 5 minus minus 7 is equal to 12, and therefore the vector is minus 8, 12. Next, column vectors. Consider this point A on a grid. As it is, we cannot give any description about point A. We don't know its position. Vectors give information about displacement. Suppose now we introduce another point B. With respect to each other, we can give some description about either of the point. If each square has a length of 1 unit, then the movement from A to B can be described. 7 units to the right and 6 units upwards. This is written as AB is equal to 7, 6, or vector A is equal to 7, 6. When written this way, this is called a column vector. We can also describe movement from B to A, or BA. That is 7 units to the left and 6 downwards. And so BA is equal to -7, -6. Or negative A is equal to -7, -6. This confirms that AB is equal to -BA. The key thing to note is that a vector describes movement from one point to another. It does not describe a single position. And so every time vector is mentioned, it must be the movement between 2 points. Position vectors. Consider the same point A alone in this grid. Can you describe it now? Yes, you can give its position as 2, 1. But how comes yet we only have one point? Actually, we have another point, the origin O with coordinates 0, 0. Notice also, when we write A, 2, 1, this is the position of A and not a vector. And most important, this position is measured from O. If you want to write the vector, you do as we did with A and B. From O, we go 2 points to the right and 1 point upwards. The column vector is written as OA is equal to 2, 1. When a column vector originates from the origin O, it is called a position vector. If we now brought B, we can find its position vector, 9 places to the right and 7 places upwards. As position vector, OB is equal to 9, 7. In summary, A, 2, 1 and B, 9, 7 are points. AB is equal to 7, 6 is a column vector. OA equal to 2, 1 and OB equal to 9, 7 are position vectors of points A and B respectively. Notice that OB minus OA is equal to AB. That is 9, 7 minus 2, 1 will give us 7, 6. An example, if OP is equal to 3, 4 and OQ is equal to -5, 1, find A, the coordinates of P and Q, and B, the column vector PQ. In the solution, OP and OQ are position vectors of points P and Q respectively, and so their coordinates are rather direct. P is 3, 4 and Q -5, 1. B, column vector PQ. Now PQ is equal to OQ minus OP, or simply Q minus P, -5, 1 minus 3, 4. That gives us -5 minus 3 is equal to -8. 1 minus 4 is equal to -3. Next, addition and subtraction of vectors. When adding or subtracting vectors, we simply add or subtract the corresponding values. For instance, if vector A is equal to 2, -3 and vector B is equal to 4, 9, then A plus B is equal to 2, -3 plus 4, 9, that gives us 6, 6. B minus A is equal to 4, 9 minus 2 minus 3. That gives us 4 minus 2 is 2. 9 minus -3 is 12. Multiplication. Now, a vector cannot be multiplied with another vector. Only scalars can multiply vectors. When we do it, every element in the vector is multiplied with a scalar. For example, if vector p is equal to 4, 12, then 2p is equal to 2 times 4, 12. And that gives us 2 times 4 is 8, 2 times 12 is 24. A half p is equal to a half times 4, 12. A half times 4 is 2. A half times 12 is 6. Next, resultant vector. Now consider a displacement from A to B and then to C. This movement can be described as AB plus BC. A resultant vector only describes the final point with respect to the initial point and completely disregards the path taken. In this case, the resultant vector will be AC or vector C. And so we say AB plus BC is equal to AC, or vector A plus vector B is equal to vector C. This is not just theoretical, it is true indeed, and we can prove it. Let us give the coordinates of these 3 points. A is 2, 1, B 4, 4, and C 12, 5. In position vectors, OA is equal to 2, 1, OB is equal to 4, 4, and OC is equal to 12, 5. We can prove that AB plus BC is equal to AC. AB is equal to OB minus OA. That is 4, 4 minus 2, 1, and that will give us 2, 3. And therefore, AB is equal to 2, 3. BC is equal to OC minus OB. 12, 5 minus 4, 4 will give us 8, 1. Therefore, BC is equal to 8, 1. AC is equal to OC minus OA. 12, 5 minus 2, 1 will give us 10, 4. Now we add AB plus BC. 2, 3 plus 8, 1 will give us 10, 4, which is also AC. And so it's true that vector A plus vector B is equal to vector C, or AB plus BC is equal to AC. Next, the magnitude of a vector. Now, the length of a vector is called its magnitude or modulus. In this figure, the magnitude of OA is the length of the line OA. Triangle OAB is right angled at B. We can use the Pythagoras theorem to find the length of line OA. So we have OA squared is equal to OB squared plus BA squared. That is equal to 7 squared plus 5 squared, giving us 74. OA is equal to the square root of 74, and that gives us modulus of OA is equal to 8.6 units. Note that the column vector OA is 7, 5, and the modulus of OA is 7 squared plus 5 squared, the square root of everything. In general, the magnitude of a column vector T is equal to AB is given by A squared plus B squared, square root of whole. Since the magnitude of a vector is its length, the quantity is always positive. For example, given that P is equal to 2, 3 and Q is equal to 5, negative 4, determine A, the modulus of vector P plus the modulus of vector Q, and B, the modulus of vector P plus Q. In the solution, the modulus of P is is equal to 2 squared plus 3 squared, the square root of whole. That gives us the square root of 13 and is equal to 3.606. The modulus of vector q is equal to 5 squared plus minus 4 squared, the square root of whole. That gives us 25 plus 16, which is the square root of 41, and that is equal to 4.403. The sum of the two magnitudes, 3.606 plus 4.403, will give us 8.009. And B, we first add vector P plus vector Q and then find the modulus of the sum. 2, 3 plus 5 minus 4 will give us 7 minus 1. The modulus of that, 7 squared plus minus 1 squared, will give us the square root of 50. That is equal to 7.071 units. Finally, midpoints. Now, a point that bisects a vector is called its midpoint. To find the midpoint of a vector, we get the point that lies halfway on the position vector. Now, suppose M is the midpoint of OA. OA is equal to 8, 6 and OM is equal to 4, 3. OM is equal to a half OA. This means that the position vector of point M is half the position vector of point A. Consider the midpoint M of the line AB in this figure. OA is equal to x1, y1. OM is equal to xy and OB is equal to x2, y2. AB is equal to OB minus OA. AM is equal to a half AB. That means X is equal to a half into x1 plus x2 and Y is equal to a half into y1 plus y2. The coordinates of M are x1 plus x2 over 2, y1 plus y2 over 2. Let's take an example. Find the midpoint M of the point P, 1, 5 and Q, 3, 7. In our solution, x1 is equal to 1, y1 is equal to 5, x2 is equal to 3 and y2 is equal to 7. The coordinates of M are 1 plus 3 over 2, 5 plus 7 over 2. That gives us M, 2, 6.
The way we teach it in university and in high school as well, and colleges, is if you fall behind, you're in desperate trouble. That if you miss a class or miss an idea or don't do your homework, you go to the next class and the teacher assumes you know it, but it's like Greek to you. And so the biggest challenge is not falling behind, and the strategy is do whatever needs to be done so you don't fall behind. Seek help wherever you can find it, from students, from student help centers, from the teacher, from the teaching assistant, wherever you can get it. Because if you fall behind, it's like you're missing a floor in the building, you're missing a brick in the wall, and you just can't build the second floor without a good understanding of the first floor.